Separated by some 10 meters, we have a 1 coulomb charge and a minus 3 coulomb charge. Where can we place a third charge such that the instant we release it, it will be stationary? And where is the voltage potential equal to 0 along the same line? So what are we asking for? Firstly, we're asking for the point where the force is 0. There is no force. And secondly, we're asking for the point where the voltage is 0, where there's no voltage. Now, the first thing to realize about the force is I haven't told you the charge of this arbitrary third particle. I'm just saying, regardless of what the particle is, no matter what the particle is, it should not have a force exerted on it when it is placed along this line wherever it's placed. This means, since force is equal to charge times the electric field, the only way for the force to be 0 with arbitrary charge is if this electric field is 0 at that point. So we're looking for the point at which the electric field is 0, in fact. Now we know that the electric field at a point can be determined by summing up all the electric fields generated by all particles. Now, because electric fields are vectors, we need to consider three main regions. Firstly, in this inner region, the positive charge will contribute a rightwards electric field, and the negative charge will also contribute a rightwards electric field, since the electric field goes out of the positive one and into the negative one. Therefore, in this middle region, the electric field will be equal to K times Q1 by R1 plus K times Q2 by R2, where these are just, we're taking the absolute value. So we're saying that it is the positive portion of the electric field generated here and the positive portion, right? That's what the absolute value is for. So the absolute value here ensures that our result is the sum of two rightwards pointing vectors. If we were doing more advanced vector mathematics, we would calculate the actual vector generated, and the formula for that, though I have not stated it before, is KQ by R cubed times R as a vector. Alternatively, you can write it as KQ by R squared R hat, where R hat is the unit vector, and these R's are just the magnitude of the R vector. But this is some advanced vector mathematics, and you don't necessarily need to know this for Science Olympiad. I will also mention just briefly that similarly the force vector is K Q1 Q2 by R squared R hat, or you could also write Q1 Q2 by R cube R vec. But to simplify things in one dimension, we just make these both absolute values, and we assign the sign based on what we know. Now, if we were in this region, then we know the positive charge will contribute a leftwards vector, and the negative charge will contribute a rightwards vector. So for that region, which maybe I'll call L, this one I'll call M, and the next one we'll call R, so this is EM. For EL, we would make the first term negative, K Q1 by R1, and we'd make the second term positive, Q2 by R2. Here we're assuming that this is Q1 and this is Q2. And so you can see, because the Q1 vector points left, we're making it negative, and since the Q2 points right, we're making it positive. Finally, in this region here, the rightwards region, the positive charge Q1 does a rightward vector, and the negative charge does a leftwards vector. So ER will have a positive for Q1, and then we will have a negative for Q2. Now notice for EM that K is positive, and therefore the only way for EM to ever equal 0 is if Q1 and Q2 were negatives of each other. If Q1, no, not even then, because we're taking the absolute value. So actually, Q1 and Q2 both have to be 0 because these terms both have to go to 0 in order for EM to be 0. And clearly we see Q1 and Q2 are in fact not 0, which means that the point at which E is 0 cannot be in this middle region. Intuitively, this makes sense. No matter where I place the charge, as long as it is in the middle region, if it is a positive charge, it will be pushed towards the right, and if it was a negative charge, it will be pushed towards the left, no matter where in that middle region it is. So we can eliminate the middle region. We know that the point at which the electric field is 0 is not in this middle region. So now we just have these two cases to consider for the left region and the right region. Now if you think about it logically, you can quickly determine that the right region will not be the proper one, because here we have a -3 coulomb charge and here we have a 1 coulomb charge, which means that immediately towards the right of the 3 coulomb charge, you'll have a very strong vector pointing right and a weak vector pointing, very strong vector pointing left and a weak vector pointing right. And as we go further away, both of them will decrease. And at no point ever will the right vector surpass the left vector. But for those of us unable to intuitively logic it out in this manner, I'll perform both calculations as well, though we should expect that our point where E equals 0 should be in the left region. So in order to go about solving this, we need to make one coordinate of position that both R1 and R2 can reduce to. So I'm going to call this point 0 and this point 10. Now if I say for the left region that this distance is R, I can rewrite the formulas in this form. Here I'm substituting in the charges, and then for the distance of the first charge, it is just R. And for the distance of the second charge, it is this 10 meters plus R. If I let R always be positive, I can drop the absolute value sign and obtain negative K by R plus 3K by R plus 10. And I forgot to mention, but these are R squares, technically. So I should put parentheses around these and square it. The formula for E is KQ by R squared, not R. Now this expression we are just setting equal to 0, and so I can divide the entire equation by K to reduce it down to -1 by R squared plus 3 by R plus 10 squared equals 0. Now I can multiply the entire equation by R squared times R plus 10 squared. And so it is essentially cross multiplying. What I will get is negative R plus 10 squared plus 3R squared equals 0. And I can expand this to negative R squared minus 20R minus 100 plus 3R squared equals 0. Or 2R squared minus 20R minus 100 equals 0. Now if I use the quadratic equation here, which I will assume you already know, we obtain two values, and of the two values, one of them is negative. And because inherently we assumed R was positive, right, we're assuming that this R is a positive distance, we cannot have a negative R value, and we know that the correct solution is R equals 13.66 meters. So our point here is at a distance negative 13.66 if we use our coordinate system, negative 13.66 meters. Now just for good measure, let's again consider the right case, even though we know there should be no solution. We'll call now this distance R, and rewrite our expression as K times the absolute value of 1 by, this will be now 10 plus R squared, minus K by the absolute value of minus 3 by, now it will be R squared. If we assume, again, R is positive, we can drop the absolute value and obtain k by 10 plus r squared minus k by 3k by r squared, and set that equal to 0. Again, we can divide out by k, and cross multiply. But now, if we solve this quadratic equation for r, we get that both solutions are negative, which contradict what we said earlier. Therefore, in the right region, there is no value of r for which E equals 0. Now let's solve the voltage problem where V equals 0. This one will be a lot simpler because V is a scalar quantity, not a vector quantity. So we don't have to worry about direction or anything, we can just use the formula directly. We know that the voltage at some point is equal to just the sum of kq1 by r1 plus kq2 by r2. And I'll make the plus a little bit more obvious and the 2 a little bit more obvious. Note that we don't have to use absolute value signs and determine the sign of the individual terms because these are scalars. So generally, when you're dealing with force calculations and electric field calculations in one dimension at least, you will want to write it in that form. And then figure out the sign here based on the situation. But for potential energy and voltage, you can just use the formulas and go. Now, in the event that the point lies somewhere between 0 and 10, we'll write kq1, which is 1, divided by x. Maybe I should keep the same convention. I used r to represent this, so I'll do it again. K1 by r minus k times 3 by 10 minus r. And this minus here, I'm just bringing it out from the q2. I could have just as easily written plus k into minus 3, but I just brought it out. Setting this equal to 0, once again, we can get rid of the k's and rewrite it with cross multiplying as 10 minus r minus 3r equals 0. And from here, it becomes very trivial to see that r equals 10 by 4, which is just 2.5 meters. Now, just for good measure's sake, let's check out the cases in which r is not right here. Let's try if r is over here. Now again, we'll have k times 1 by r. That will remain unchanged. But now we'll also have minus k into 3 by 10 plus r. Because here we're considering r as the positive distance from 0. So maybe we shouldn't write this as r, but rather this length as r. Now setting this equal to 0, again, we can cross out the k's, cross multiply, do all the usual stuff. And we get 10 minus 2r equals 0, or r equals 5 meters. And remember, since r was the positive distance, but since it was towards the left, we'll write minus 5 meters. Finally, let's consider the case where it's towards the right, so I'll call this distance my r now. I have k into 1 by 10 plus r minus k into 3 by r equals 0. Cross out the k's, cross multiply, we get r minus 30 minus 3r equals 0, or minus 2r minus 30 equals 0, or simply r equals 15 meters. And we have to add that to this 10 meters, we get 25 meters. So if we are to place a point at this x-coordinate, some particle, we know it will not move immediately. Of course, it might influence these two particles to move, and once those two particles start moving, then that point might move. But if these two particles are being held still, then if we place a third point at this particle, it should not move. And these are the points of zero potential, which are useful when we're dealing with circuits and we're talking about electrostatic charges, forces, just a general metric of potential energy. These points are where our voltage is 0.